Last week, Eric was the expert. Today, I get to be the expert. We're talking about probability theory, and I have a probability puzzle. I'm going to challenge Eric with it. He hasn't heard it. Um,
Yeah, I
so,
should say I'm extremely nervous about this.
okay, good, good.
Okay.
Because I was very nervous about the physics
Yeah,
stuff and the Big Bang stuff. So,
that's right.
okay,
That's right. So turnabout is fair play.
right. Yeah, all you scientists, you know things and you know facts. So, like, about time. Um, so, first, though, we'll start with a related probability puzzle, which is not controversial. The one I'm going to share is controversial, which is so cool. Uh, a probability puzzle where like mathematicians don't agree on what the answer is. But the non-controversial one actually was historically controversial, and that's the Monty Hall problem. So Eric, I was wondering, what do you know about the Monty Hall problem, and yeah, how would you go through that reasoning?
Yeah, right. So let's see. So Monty Hall was the original host of the Price is Right, which was a game show on television. And I think, I mean, so if I'm remembering correctly from my childhood, near the end of each episode, there would be a special round where a contestant would be offered a choice to choose one of three. I mean, we're going to call them doors, but really, I think they were curtains. Uh, offered a choice of one of three doors, and behind one of the doors would be, I think, a new car. The other two doors, one of them had a goat, and a third one had like some medium level of prize. But in the simplified version of the Monty Hall problem, there are three doors, and behind one door is a new car, and behind the other two doors is nothing. Okay, so it's just a slightly simpler version of the problem. And so the contestant was allowed to pick any one of the three doors uh, at the start of the interaction. But rather than simply revealing whether they had guessed correctly, Monty Hall would then choose one of the two doors that the contestant had not guessed and open it to reveal that that door did not have the new car behind it. Okay, so at that point, the contestant was now confronted with two remaining closed doors, one of which had a car behind it and the other which did not. And Monty Hall would ask the contestant whether they wanted to change their initial guess and change their guess from the initial door to the new door. And I think historically, the majority of people did not change their guess. Okay. And the reason is simple enough. You know, if you put a normal person who isn't an expert in probability in a situation like that, they sort of vibe out. They use the force to determine, which door the car is behind. And having made that initial choice, they're reluctant to change their minds halfway through the interaction. And I think we see this. I mean, we see this in the real world too, right? I mean, even after, if you make a choice at some point in your life about literally anything, it's always, I think, a little harder to change your mind than to simply stay the course. But anyway, so most contestants chose not to change their mind, and they kept stuck with the original door. But the Monty Hall problem, which is sometimes called the Monty Hall paradox, is that in fact, you should literally always change after they've revealed which door doesn't have the card. You should always change away from the door that you initially picked. So, Sam, does that agree with your understanding of it?
Yes, except the name of the game show was like Let's Make a Deal.
Oh, yeah, that's
Yeah.
okay. Thank you. Yeah.
Yeah.
Thanks. Okay.
Yeah, but otherwise, exactly right.
Okay. And so, and then actually, I have to admit, the first time I heard this, and maybe the 10th time I heard this, I didn't really understand why you should change. Because from the contestant's side, or from the side of someone who isn't and hasn't thought about the problem in depth, once they open the door that doesn't have the car behind it, you're confronted with two doors, one of which has a car behind it and one that doesn't. And so the chances are just 50-50. And so you're not committing a mistake by just sticking with your initial choice. And so to understand why you need to change, I actually, maybe 6 months ago, I actually read a book that talked a lot about this particular issue. And so I thought a lot about it, and I thought a lot about it, and gradually over time it became clear. Okay, so to explain why you should always switch doors, I just want to start with a variation of the Monty Hall problem. Let's imagine that instead of three doors to start with, there are 1,000 doors to start with. Okay, so at the beginning of the interaction, you choose one of the doors, and you know that the chance that a car is behind one of those doors is 1 in 1,000, right? But then Monty Hall opens 998 other doors, leaving just one. Okay, and at that point, I think at that point most people would simply assume that that new door that there's only two doors left. I think most people would switch doors at that point. What do you think?
I think probably most people would, but yeah,
Right, because Monty Hall knows where the car is. So he opens 998 doors where the car isn't, and he leaves one closed. I think most people would say, oh, the car has got to be behind that door because the initial chance that I guessed right was only 1 in 1,000. But Monty Hall has all the information.
right,
So I think if there are 1,000 doors, then the idea is all that excess probability, if you like, flows into the door that Monty Hall left closed. And so you absolutely should switch.
right,
And that is the correct logic.
right.
So now let's go back to the case where there's just those three doors. So this one, because it's only three doors, it's less obvious. But I think part of the answer here is that Monty Hall has Monty Hall has literally all the information. He knows where the car is. And so it's less obvious why all the probability for the car should flow from the open door into the unopened door that you didn't pick. And in other words, why didn't the probability flow equally into the two closed doors? It's less obvious in that case. So for me, the final piece of the puzzle was thinking about what Monty Hall sees. And also, I have to admit, there's also a piece of the puzzle here where it depends on what you think Monty Hall's job is, right? So if you're imagining that Monty Hall is trying to hide the location of the car from you, then I guess 50-50, it seems natural that after he's opened one of the doors, the final result is 50-50. If you instead assume, okay, this is the interesting part, right? Because Monty Hall has to follow certain rules too, right? From his side, he sees where the car is. You get to pick one of the three doors, and then he sees where the car is. He is obligated to open the door that you didn't pick and behind which the car is not. So Monty Hall doesn't have any discretion in this situation. He has to open one of the three doors.
Unless you pick the car, then you can choose arbitrarily.
Oh no, that's right. So if you pick the door that has the car initially, he's still obligated, right? He's obligated in that case to pick one of the two doors that you didn't pick. But in that case, he has the freedom to choose either door.
Right.
Okay. But so you could think of it as, oh, he's trying to hide where the car is. But you could equally well think of it as he's trying to tell you where the car is. But his only option is to open one of the three doors, right?
Right.
So if in other words, if he was told you have to convey as much information as possible to the contestants about where the car is, but the only thing you can do is open a door, then the problem is identical. Do you agree that the problem's identical and that's an identical
That's a really
interpretation of
interesting point, right? About reading into his motivations. Yeah.
yeah, yeah. I mean, in other words, I think yeah. So I feel like by trying to decide what Monty Hall's motivations are, it clarifies. Despite the fact that he's just doing a job, I mean, he could be replaced by a computer algorithm that's just following a set of instructions. But I think at the core of the Monty Hall paradox is partly you're imagining that he's trying to hide the car from you. But if instead you imagine that he's trying to tell you where the car is, then I think you'd be more likely to switch
Yeah.
because he
Right.
knows where the car he knows where the car is, and so you should take his advice.
That's great.
I mean,
He's
we
not
still
trying to
haven't
trick
talked.
you. Yeah.
He's not trying to trick you, just the opposite. So part of the puzzle is that there's a human being you're interacting with another human being, and so that person's motivations are part of your thought process. Mathematically speaking, Monty is very constrained, and his motivations are irrelevant to whether you should switch or not, assuming you want the car. So this is all the background. I haven't done any math yet, or I've done extremely almost no math.
Right.
So should I do the math for the Monty Hall problem in a kind of straightforward version now?
Sure, if you want. Could I add though? I'll add a couple things about what you're saying.
Yeah.
I agree. Is a really beautiful explanation of it and added a lot of dimensions that I hadn't really thought through. But to me, uh, if Monty Hall were deciding randomly, if that were the algorithm, then it wouldn't matter if you switched or not because you wouldn't be getting any information
Oh
from
wait,
Monty Hall's.
I'm sorry. He decided randomly. Wait, subject to any rules, or he just could he open a door with the car behind it?
Yeah, that's what I'm saying. I mean,
Oh,
if the
so
algorithm was that Hall, you pick one door, there's two unopened doors.
okay,
If Monty Hall randomly picked one of those two doors
yes.
and opened it, then you're not getting any new information. I mean, you're getting information that it's not in the door that he opened, assuming it was empty. But
Oh,
then the
wait,
probability would go evenly to the
wait,
two
wait, Sam. I
unopened
think you're
doors.
skipping over a point, which is that let's say the audience can see the car, but the contestant can't. Right? In other words, if the contestant can see where the car is, obviously they'll switch.
Yeah,
I guess I'm not understanding the change you're proposing.
yeah. So, um, what I'm saying is, you were saying, why does the probability all go from the door that Monty Hall opens, the empty door? It
Yeah,
all goes to not your door. None of it goes to your door. It all goes to the remaining unopened door. And what I'm saying is, it does all go, but it goes because of what you're alluding to, because of our knowledge of how Monty acts.
yeah.
If we knew nothing about how the show worked, if Monty were like an alien, or if Monty were making a random choice, if he were flipping a coin between the two unopened doors, then that wouldn't happen. So I think the reason people get fooled is that they think you're gaining in lots of setups like that, you wouldn't gain anything new in terms of information. It's only
Oh,
because of this additional premise that you know Monty will open an empty door
oh,
and you
so
know he
right.
knows where the car is.
So we're working right. So in other words, you're saying there's probably a whole realm of everyday things that we encounter that are similar but not identical to this situation. And so so the normal person just or the person who hasn't thought a lot about this, they're extrapolating from their own experiences without recognizing that this is a atypical situation.
Right. So say that you and I were the contestants on this show and I guess door one and it's empty. Or no, so I guess door one and then you guess two or three. You don't know where the car is.
Right?
And then Monty, the game show host, opens your door, shows that you were wrong, and asks me whether I want to switch. It doesn't matter if I switch or not. The probability flows evenly into my door and the other unopened door because you didn't know
Oh,
which
okay.
one which one had the car. So
Okay.
it's only because Monty knows where the car is and also is committed to opening an empty door.
Right.
That's why it all goes towards that unopened door.
Right. So the key feature of the problem and the feature that's a little bit unusual is that Monty has information you don't, and then he's interacting with the doors.
Yeah, right. So there
Okay.
was, okay, so why don't you go do the math? I think that's a
Right.
good
So
time
the
to,
math, and I'll try to do this quickly and simply, um, is okay. So when all three at the start, when all three doors are closed, the chance that the car is behind one of those three doors is 1 out of 3. Okay. Once you pick a door, um, this problem immediately breaks into two separate situations, which you mentioned a little while ago, right? So now let's look at it from Monty Hall's perspective, okay? Because he's the next person to act anyway. So one there's a 1 in 3 chance that you pick the door with the car behind it. And in that case, Monty Hall can open either of the two other doors and doesn't reveal any new information. Okay. So on the other hand, there's a 2 out of 3 chance that you didn't pick the door with a car behind it. And in that case, Monty Hall opens the one of the other two doors, and at that point, the car is definitely behind the door he didn't open. Okay, so there's a 1 in 3 chance that the car, from Monty's perspective, there's a 1 in 3 chance that the car is behind the door you initially picked, and then there's a 2 in 3 chance that the car is behind the door that he left closed. And so the probability actually shouldn't depend on who's looking at the situation. So the probability is now twice as high that there's a car behind the door. Let's see. There's a car behind. You should. Okay. Right. So you should switch because there's a 1 in 3 chance that there's a car behind the door you initially picked, and there's a 2 out of 3 chance that there's a car behind the door that Monty left closed. How's that?
Right, right. And then when Monty opens that door, you don't learn any new information about your door. It's still one third
Oh,
because
wait, wait. Say,
he has
oh,
an
yeah.
empty door to open and he's going to open it no matter what. So
Right.
you don't find out anything relevant to your choice of door, but you find out something very relevant to the other door, the other two doors.
Yeah, yeah, yeah. So to me, I think again, it comes down to the fact that Monty Hall knows where the car is. So one time out of, I mean, if we maybe we should go back to the case of 1 out of 1,000, right? So in the 1 out of 1,000 case, you've guessed correctly initially, one chance out of 1,000. But then Monty looks at the 999 other doors. Oh, right, right. So actually, so there are still two categories of there are two possibilities here. One is you did guess correctly, in which case Monty can open 998 doors, but it doesn't move the car. But then most of the time, 999 out of 1,000 times, the car isn't behind the door you picked, in which case Monty's about to tell you where exactly the car is, right? So most of the time, when Monty opens 998 doors, he's telling you exactly where the car is.
Yeah.
And so you should definitely switch.
Okay. Beautiful explanation. Yeah, I agree. And
Okay.
there's a really great historical and kind of uh, the way that this came to light, I guess, was that Marilyn Vos Savant had a column for
Oh,
Parade
okay.
magazine, and she wrote this, which is the correct strategy. You should always switch. And so many, so many people, including like like hundreds of math PhDs,
Oh, right.
argued with her and
I heard about this.
minimized her and diminished her and said, you don't know anything. And so there's definitely a gendered
Oh,
aspect to their
do you want to
criticism. And she
do,
was totally right.
I stepped on your point that this is a gendered criticism, but do you want to explain who Marilyn Vosavant is or was?
Well, she was a columnist for Parade, and she is the person who's had the highest recorded IQ in human history. Is that right?
Oh, I don't
Or
know
at
that
least
part
at
of
the
the
time.
story. I just know that she was a columnist on for Parade who would answer various questions, and the premise was she was an extremely smart person
Yeah,
who would answer your questions.
her IQ was 228.
Oh, I don't know that I remembered that, but okay.
Yeah, no, she was like in the Guinness Book. I don't know if she still is, but yeah, no, she's extremely smart. And yet, there were many, you can only imagine if the internet existed at the time. There would be thousands more of,
Yeah, that's right. She was the
critiques of
victim of a
her.
very early flame war, actually,
Yeah,
is the way you might put it.
yeah, which is, she was right. So they were wrong. Uh, so new puzzle, and it's good to reflect on this question of did you get new information in this puzzle, which is why we talked about Monty Hall.
Okay, I mean, I have pen and paper. Am I going to want it? Or,
You
or
might
are,
want
are
you
our
might want
listeners
to. I
are our
don't
listeners
know.
going to want it?
Yeah, I wish I could like draw on my screen. We're not going to do that.
Okay.
So this is called the Sleeping Beauty problem.
Okay.
And here's the scenario. So Sleeping Beauty is subject to a human research experiment. And she's explained what's going to happen to her on Sunday. So Sunday, she shows up for the testing and they explain what I'm just about to explain to you.
Okay.
Okay. So she's going to be given sleeping medicine, let's say, and put to sleep.
I'm already getting uncomfortable about this, but okay, go on.
Okay. No, no, you should
How
be.
uncomfortable am I about to get?
Um,
Like we're
well, I
getting, I
don't
mean, look,
know.
it's consensual, but we're still okay. Anyway, it's
No,
she's
no,
agreeing to this.
she's agreed to this. It's like sleep study or whatever. Um,
Okay,
uh,
she's getting paid. She's getting paid good money.
okay, sure, sure.
Okay, that makes me feel better.
Okay, good, good. Um, so she goes to sleep on Sunday, and then on Monday morning they flip a coin, a fair coin. It's either heads or tails. If
Okay,
it's heads, they let her sleep until Tuesday,
okay,
and then Tuesday they'll wake her up at noon. She'll be in a just a featureless room. She'll be awake for an hour, and then she'll go back to sleep. Maybe there's a pill there for her to take.
okay.
And that pill will erase her memory of having woken up.
Oh boy. Okay.
And then she'll wake
Okay, wait,
up.
wait. So
Yeah,
this is sort of a science fiction scenario, and but we've stipulated that that she consents to it and she's being well paid.
yeah.
All
And
right,
she's
go
just
on.
forgetting an hour, like waking up, and it's an hour in a featureless room, and she goes to sleep. So then she goes to sleep on Tuesday. In this case, this is the head scenario. So she woke up on Wednesday morning. She forgot about being woken up on Tuesday, but she was just awake in a featureless room for an hour. So she's told the experiment is over on Wednesday, and she's given $1 million.
Oh,
So does
okay.
that make you feel better
All right,
about?
right. So let me make sure I understand. So she goes to sleep on Sunday. She wakes up on Monday. She's awake for an hour. She goes to sleep on Monday. She wakes up on Tuesday. She's awake for another hour.
Well, uh, so we're talking about the
Oh,
heads
wait, no, there's
scenario
coin
now.
flips. There's coin
Yeah.
flips.
So the coin flip happens on Monday. And if it's
Yeah.
heads, she's not woken up on Monday.
Oh, okay.
She's
All right.
woken up on Tuesday.
Okay. And then what
And
happens on
then,
Tuesday?
so she's awake for an hour. She takes a pill that makes her forget that she has woken up and she goes to sleep again. She wakes up on Wednesday. Of course, the last thing she remembers is Sunday night. And they say, the experiment's over. Here's $1 million. I
Okay.
would do this for $1 million.
Well, you haven't told me what the question is, though.
Well, we haven't gotten there yet.
Okay.
That's one tree. That's one branch of the tree. That's if heads is flipped on Monday.
Oh, if heads is flipped on Monday,
Right.
then
She's
this is
never woken up.
then all these steps follow if heads is flipped on Monday.
That's right.
Okay. All right.
Okay. So now, if tails is flipped on Monday, then it's as you just described. She's woken up on Monday for an hour. She takes the pill that makes her forget. She goes to sleep. She's woken up on Tuesday again for an hour. She's awake for an hour. She takes the pill that makes her forget. She goes to sleep. And she wakes up on Wednesday.
Okay.
And then she's told, of course, still the last thing she remembers was Sunday. And she's told that the experiment is over and she's given $1 million.
Okay.
So basically, in short, she goes to sleep on Sunday no matter what. If it's heads, she sleeps on Monday, is woken up on Tuesday, and then the experiment's over. If it's tails, she wakes up on Monday and wakes up on Tuesday, and then wakes up on Wednesday. And crucially, she's given this forgetting pill. So on Tuesday, in the tails case, she's already woken up on Monday, but she doesn't remember.
Okay.
And then on Wednesday, she doesn't remember any of her
So
wakings.
so the common features in both scenarios are she goes to sleep on Sunday. She goes to sleep on Sunday. She wakes up on Wednesday and the experiment is over. Um, there's a single coin flip during the experiment, not two.
That's right.
Okay, so there's a single coin flip on Monday. And in both scenarios, is she awake on Tuesday? Is she
Yeah.
awoken on Tuesday for an hour?
Yes.
But in one scenario, she's not awoken on Monday, and in the other scenario, she is.
Right.
Okay, I think
So
I've
that's
got
the
it.
setup. And
Okay,
now the probability question is when she wakes up. So she goes to sleep Sunday night. She wakes up. what should her probability that the coin came up tails be
Wait, when she wakes up on which day?
whenever she wakes up? So she goes to sleep, from her point of view, she goes to sleep on Sunday. She awakens to find herself in this room. What's her probability that tails was flipped?
Oh, wait. So this isn't the question. In other words, she doesn't wake up on Wednesday. The question is when she's awoken on either Monday or Tuesday or Wednesday,
Well,
what
not
what
not
was the
Wednesday. Not Wednesday. We can imagine, there's like a different color. Uh, the walls are a different color. They're
Oh,
saying
oh,
it's over,
okay.
it's over. So this is
Oh, okay.
it's she knows
So
it's either Monday or Tuesday.
okay, so she wakes in one of these hour-long windows of wakefulness, and it's either Monday or Tuesday. And so it seems like so if the coin came up heads, then she was woken up on Monday and she was woken up on Tuesday. If the coin came up tails,
That's a reverse, actually.
oh,
If it comes
okay.
up heads, only
If
woken up on
only woken up on
Tuesday.
Tuesday. If the coin comes up tails, she's woken up on Monday and she's woken up on Tuesday. And the question is, and during the one of those, any one of those 1 hour
Yeah, she doesn't know.
blocks,
She's just woken up. She
she's
has the
woken
experience
up
of waking up.
and she's asked, what is the question to her?
What is the probability of tails?
What is the probability of tails?
And so it's controversial. There's two answers, there's a fierce debate between two answers.
Well, can I give the answer that feels obvious to me?
Yeah, that's why I'm asking you. I
Right.
want
I
to
mean,
know.
the obvious, I mean, okay, let's make sure we understand the language of the question. The language is, what is the probability that the coin came up tails?
Yes,
That's the question. It's a question about the recent past.
right.
And and oh, I see. Right. So the naive answer would be just 50-50.
Yes,
But I guess I could, right? So because it's a coin and it's a fair coin, so the chance of a coin coming up tails is 50-50. On the other hand, I guess the objection that sometimes comes about would be, well, if the coin came up tails, then there are two opportunity. Wait, is she asked during every period of wakefulness? Is she asked this question?
yes, yeah. So she
Oh,
can't.
okay.
Yeah, it's an identical experience.
So in the case where I think you said the coin comes up tails, she wakes up on Monday and she wakes up on Tuesday.
That's
And
correct.
so she's going to get asked this question twice.
That's right.
Okay, all right. Right. I mean, so the naive answer is 50-50. And maybe you can tell me the other answer.
Yeah. So the other answer is two-thirds.
Okay.
And so the argument for the naive answer is she went to sleep Sunday believing that this was a fair coin. When she's woken up, she's gotten no new information about the coin. Like she hasn't learned anything. Because no matter what, whether it's heads or tails, she knows she's waking up in this room. She knows she's going to have that experience. So when she has that experience, she hasn't learned anything. And so she shouldn't change her probability. She should still say probability of tails is zero point 0.5. But the other answer, and maybe the easiest way to think about this, like you're doing 1,000 doors for the Monty Hall problem, if you did this many, 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 many times, in
Well,
the long run,
can we specify? I think we should be clear about what the thousand door extension would be in this case. So if the coin is heads, she's allowed to sleep on Monday and she's woken up on Tuesday and then sent home on Wednesday. Um, if the coin flip is tails, though, then she's going to be there for, let's say, 100 days.
right,
They're going to make sure she's well fed and everything, but she's woken up every afternoon for 100 days and
right,
asked and administered this memory erasing drug. And so it feels like in that case, the probability is extremely high that the coin came up tails.
yeah, that's
Oh,
right,
right. Yeah, I want it to be heads, but tails. So, right, because if the coin came up tails, then, right, then there are all these extra opportunities for her to answer this question.
right.
Yeah. And you're saying that and you're in the process of telling us that people who do this for a living, they actually don't agree on what the correct answer is.
That's correct. Yeah. And some people say you don't learn any new information. And so you shouldn't change your probabilities. And other people say, I mean, to motivate the tails answer, if she were asked to bet, if she knew every time that she was woken up, she had to bet on her odds,
Right.
then in the standard case, two-thirds of the time she wakes up, it's our tails cases, then she should bet on the odds of two-thirds for
Yeah.
tails.
So that feels key to me because I was thinking in preparation for this episode, I was thinking, what is probability or what is the important feature of these probability problems? And it's always probability is a way to assess. It's a tool to assess what you should do in the future or what you should do in the present to benefit, right? So I think asking whether right. So giving her some agency where she will win money if she guesses correct. Then suddenly the answer seems obvious. It seems like she will have she should guess tails because if the coin was tails, then oh wait, does she get paid for each right answer?
There you go. There you go.
Right,
My friends wrote a
right.
paper on that, which is sort of like it really depends on how you're rewarded or penalized for accuracy. Is it every moment, like every waking that she's asked to do it, or
Yeah, right.
does she just know
So
she's betting once per experiment?
no, but I mean, right. But if she's given, let's say, $1 million for each correct guess, right? And so that means that if the coin is flip is tails and she guesses tails, that means she comes out of the experiment with $2 million.
That's right.
Okay.
Yeah, yeah.
So in that case, I mean, it seems obvious that she should guess tails because there will be a better outcome for her.
Well, yeah, although she'd also be if she's betting, she's risking her own money too. So she could be risking twice too. So
Oh,
I think it really depends on what odds she's getting for her bet.
well, can you unpack that a little more? So
Yeah.
let's say that she's going to get a $1 million either way. But let's say that in addition, for every right answer about the coin, she's going to get another million. Okay. So at the end of the experiment, if she guesses heads, then she walks out with, I guess, uh, oh, uh, if she guesses heads and she's right, she walks out with $2 million. If she guesses heads and she's wrong, she walks out with just the million that she was going to get anyway. If she guesses tails and she's right, she walks out with $3 million. If she guesses tails and she's wrong, she still walks out with $1 million. Does that all add up to you for you?
I mean, yeah, I agree with the math there.
So it seems like she should guess tails no matter what.
Right. In that particular scenario, for sure, because it's a greater prize pot for guessing
Oh,
tails.
and so it's a larger pot of
Right. So
money.
even if it were a 50-50 chance, like let's stipulate it's a 50-50 chance probability, that's the
Right,
right answer. If
right,
you get $2 million, if tails happens to be right, you should just guess tails,
right.
even if you think it's a 50-50 chance. So I think that particular way of asking it doesn't convey the odds. But so if she thinks it's 50-50, then she'd be willing to risk $100 to get $100, every time she's awoken. But most of the time, if she did this experiment, let's say instead of having it be 100 days, let's say she did this iteration of the experiment 100 times, like Sunday, Monday, Tuesday, Wednesday, just that
Right.
thing, but she did it like 100 weeks in a row,
Yeah.
right? Well, over overall, she'd tend to have close to two-thirds of her wakings up would be tails.
Yeah.
So if she risked $100 to get $100 back, if it was heads, in the long run, she would lose money. So she would should say, no, no, no. If I put $100 for heads, I want $200 if I win. So she'd want
Yeah,
favorable
so
odds.
so to the extent that probability is about trying to figure out what a smart person should do in a given situation, then 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 the probability of tails is two-thirds, and end of story. So I feel like this is getting to what how you define probability.
Yeah.
But can you, I mean, but tell me, I mean, is this what philosophers, when philosophers disagree about whether the probability is one half or two-thirds, is this really a disagreement about what probability is?
Yeah, I mean, certainly, I mean, it's being presented in a Bayesian framework in terms of subjective probabilities
Oh,
that they
wait. Hold on, hold
are
on.
estimate. Okay.
Hold on. You just used two expert words, neither of which you've defined. I don't know if you want to go down this road, but use the word Bayesian and use the word subjective probability.
Yeah.
I mean, we've
Yeah.
intentionally been avoiding the word Bayesian. Certainly I have.
Okay.
Um, so I think maybe, I don't know about you. I think it might make sense to continue avoiding the use of both those words
Okay. That's
for this
fair. So
episode.
just personal probabilities. Just what do you think? Like I have what's your people have subjective probability that God exists or that there was once
Oh,
life on
actually, we
Mars?
can
Just
unpack
what do you
subjective.
think?
We maybe, I mean, I don't mind unpacking. I want to stay away
Yeah.
from the word Bayesian, but we can unpack this concept of subjective probability. Sam, what is subjective probability?
Sure. Well, it's just your personal opinion and well, people who will not be named would say that you could uh, elicit what someone's subjective probabilities are by inviting them to do a series of bets and what kind of risk they would take based on a certain outcome shows what they really think in terms of it's their estimation of the truth of something. And so
Oh,
this would be
wait. So
different
it's
from
their estimation of the truth of something.
right. So if I think
Okay.
there's a 70% chance that at some point there once was life on Mars, like that might be my personal guess. And I think we ask each other these questions all the time.
Yeah.
Yeah. And it's just uh, the same way that a meteorologist says that it's a 50% chance of rain, that they're sharing that with from their analysis, they think that uh, they're that half that I don't know, there's a 50% chance. That's what they'd be willing to bet on for it raining that day.
Okay. So a subjective probability is, it doesn't mean that you've made a thorough scientific study of a situation. An uninformed person can still have a subjective probability estimate for pretty much anything.
Yeah,
Okay.
absolutely. I think this is how we model or represent the world is in terms of these kind of shifting probabilities. Like we're pretty certain about that, or we're really certain about that, or I don't know, that could happen.
Okay.
The Mets could win the World Series. Like I think we convey to each other what we think is likely and not likely all the time in normal language.
Okay. All right.
That's
So
what we're talking
subjective
about.
probability is just the chances that anyone would assign to anything, regardless of whether they've made a careful study of it or not.
Right.
So wait, so in the, but I mean, so in the Sleeping Beauty problem, Sleeping Beauty, I mean, presumably Sleeping Beauty understands exactly what's going on. I mean, Sleeping Beauty understands what's going on. I mean, what do you think? I mean, where do you land on this? I mean, what is like, let's say you're Sleeping Beauty. What do you guess when they wake you up?
I guess two-thirds.
Oh, so you guess tails.
Yeah. Yeah. I think it does raise your probability. I think just in virtue of waking up, that's an experience and that counts as evidence that, sort of indicative of it's a waking up experience. And there's more of those experiences if it's tail. So I think that waking up is evidence. Even though you're certain it's going to happen, I still feel like it counts as evidence.
And what do people who disagree with you argue or put the emphasis on?
Well, they argue that you're certain that you're going to be woken up no matter what. So if you're certain it's going to happen, how can it be evidence for a specific outcome? I mean, it's hard. My buddies wrote a paper on this, which I thought was great, which was they thought that there was a real ambiguity here between how you measure reliability. So how do meteorologists get evaluated for their effectiveness. And it's actually debate. And this is a really cool thing where in philosophy, people cite meteorologists because meteorologists have studied mathematically how should we be assessing ourselves, which
Oh,
is kind of the
interesting.
same question of like how should we all strive in our probability assessments to be accurate? So it's this what counts as accuracy? If I say there's a
Oh,
60% chance that it's going to rain and it rained, was I right?
oh, oh,
You know?
interesting. Yeah, I mean, right. So these numbers, which meteorologists throw around all the time, there's an 80% chance it's going to rain. There's a
Yeah,
30% chance it's going to rain. What does that mean? Um,
right.
actually, and since I have to drive a fair amount, so like if I have to do a 2 hour drive every once in a while. And and so I look at the weather reports to try to decide which day is the best day during the week for me to
Mm,
make that drive. Um, so I guess it's sort of all relative, right? So I mean, if it says if there's a 30% chance of rain on Wednesday and a 90% chance of rain on Thursday, then I guess I'll probably make the drive on Wednesday because I don't like driving in the rain. But I mean, but what do those numbers actually mean?
right.
Especially when you're living in New England.
Well, we get so petty. We're like, there's only a 20% chance of rain and it rained. But were they wrong? They said there was a 20% chance. So there's a whole literature on that. And my buddies had this article on Sleeping Beauty where they argue that if you have, it's like it's the difference whether is the meteorologist like, is their accuracy measured like, I don't know, every minute of the day? Or is it just once per day? And in a way, that's like if Sleeping Beauty were asked to bet once on the whole experiment, then should say 50-50. But if she's asked every time she's woken up, then she should bet two-thirds. So,
Yeah, I mean, I mean, I feel like what we're getting at here is that probability is really a way to compare different possibilities, right? In isolation, it's very hard to like if I say there's a 30% chance of rain on Tuesday, it's very hard to say what the heck that means. But if you're comparing Tuesday to Wednesday, then that feels like a useful piece of information. Like it's more likely to rain on Wednesday than Tuesday, for example.
right. And then maybe that's one reason why that like kind of n=1 problems that you find, for example, in astrobiology are very challenging, where you only have one data point,
Oh,
one Earth.
astrobiology being the study of life on planets or in other solar systems, but n=1 being we only know for sure that there's life on Earth.
That's right.
N=1.
Yeah. Okay, sorry. Well, let me just now that we're talking about your domain a little bit,
Oh,
um, let me let me pose one last puzzle to you, which is, do you have any interest in the two-thirds answer? Are you attracted to that at all?
well, I mean, it sounds like the right answer to me if that's what you're asking.
Okay, yes, that's where I'm going. Be careful when philosophers ask you
No, I mean,
questions
I
like
think
this. You
I
should
mean,
be nervous.
the right. No, I mean, I think I agree with what you just claimed was the right answer, or in your opinion,
Yeah.
which is
Okay.
that since they wake her up twice in the tail situation and only once in the head situation, then the probability of tails is two-thirds.
Yeah. Okay. So here's an argument that if you say two-thirds, that you have to endorse the many worlds interpretation of quantum mechanics. So, and the many worlds interpretation of quantum mechanics, now you get to correct me if I'm wrong, it's that in every quantum event, there's sort of a splitting or branching of the universe such that there's one version of the universe where it went one way and another universe where it went the other way. Many
In
worlds.
short, yeah, the many worlds interpretation of quantum mechanics is a description of the universe and experimental outcomes that is entirely in terms of probabilities, but a way of thinking about it which can't be disproved, which is completely consistent with every experiment, which is that instead of saying that, oh, let's say you flip a quantum mechanical coin, and there's a 50-50 chance of it coming up heads. One interpretation would be, oh, in our universe, half the time it will come up heads and half the time it will come up tails. There's an alternative, equally valid interpretation of quantum mechanics that says that the universe splits at that moment, that there's a that there's an that there's a universe that branches off that where the coin comes up heads, and there's a 50-50 chance that you are in that universe, and there's a other universe that's created where the coin comes up tails, and there's a chance you're in that universe. And that with literally every quantum interaction has a range of possible outcomes. And so with every possible quantum interaction, the universe grows in its multiplicity without limit, so that there's essentially an infinite number of universes, and that's what these probabilities describe, just your path through this infinite branched set.
Okay. So, how many versions of Eric are there if this is true?
Well, I mean, right. So obviously an infinite number.
Okay. So then, if you think there's any positive probability that the multi-worlds interpretation is true, imagine the Sleeping Beauty problem where she's told, well, we don't know if we're not going to tell you if we're actually going to do the experiment. But if we do the experiment, we're going to wake you up an infinite number of times.
Oh,
That infinity would wash out however improbable she thought it was that the experiment would actually happen. And she should be completely positive when she wakes up that the experiment is happening.
wait, let me make sure. Let me make sure I understand. So, are we still proposing the head tail flip on Monday?
Right. Except maybe we'll say there's an infinite. Now it's God who's doing it. There's an infinite number of days if it comes up tails.
But so if it comes up heads, then she is woken up after a hypothetically infinitely long nap.
Yeah.
And if it's tails, then she's woken up every day for a philosophically infinite number of days.
Yeah. Yeah.
Um,
Or really, we could say duplicates. You could do this also with duplication. So a copy of you will be made, and then she's not sure which one she is.
um, I'm not sure. I'm not sure I'm following, but your argument in that case is that she should definitely guess tails.
Uh, yes, yeah. Even if it were if it were unfair coin and it were very, very, very unlikely that tails would happen. So let me do it in terms of duplication because the time thing is weird.
Okay.
So, and actually, this is called duplicating beauty. That same setup, except she's told if heads comes up, your life will continue as normal. But if tails comes up, and this time it's got to be a God, God's going to duplicate you atom by atom in an exact, let's say duplicate the whole Earth. And so you'll be
So in
there.
one of these quantum
You'll never know.
multiverses.
Sure, sure.
Sure.
And then, so then there would be two instances of her experience. I mean, she couldn't tell if she was the duplicate or the
Well,
original.
I mean, I mean, there's no way to communicate between these
Right.
sort of different leaves of the future.
Yeah.
So, yeah, I mean, there's literally no way to exchange information.
Yeah. That's right. So she wouldn't be able to tell. And so if you think in the normal case, you should say two-thirds for tails. It seems like in this case, you should say two-thirds because there's more experiences of hers if tails comes up.
Oh, yeah. I mean, so this is a sort of question that I regard as the sort of question philosophers like, because it's sufficiently detached from practical stuff that it feels unanswerable to me.
Yeah. Right.
I'm,
So, but I mean, but in general, let's just go with the concept of the Sleeping Beauty experiment. This idea that there's more instances of the experience if it comes up tails. So now, instead of the coin flip, we're considering what's the chance that many worlds interpretation of quantum mechanics is true. If it is true, each of us have, infinite number of experiences that we couldn't distinguish, right? Us or our duplicates in any of these universes in the quantum multiverse or whatever. And so we should be, even if it were initially very improbable, we should be almost certain that it's true.
okay. I mean, I think I see what you're getting at. You're arguing that if there's a chance that many worlds interpretation of quantum mechanics is true, no matter how small, that then we should believe that it's true. Is that what you're arguing?
Exactly. Yeah.
Okay. Yeah, I mean, I've heard philosophical arguments along these lines. To me, it sounds a lot like Pascal's original argument for believing in hell. Do you know, you must
For,
know
for
this, you must know this argument.
for believing in hell or for believing in God so you don't go to hell?
Oh, I guess either way.
Okay.
So wait, so it's Pascal's argument for believing in God?
Right.
Okay.
Right. Because even if it's a small chance that God exists, if God does exist, we have an infinite reward, an infinite number of
Oh, isn't
lives.
it funny that I remembered it as you need to believe in hell because if there's even a tiny chance that it does exist, then you'd better believe in it because
Yeah.
the
Well, you better
consequences of
believe in
not
it and
believing
do
in
the
it are
thing you
so
need to do
horrible.
to avoid going there. You know.
Yeah.
Yeah. It's just the opposite way of talking about it.
Right, right. So, yeah, but I mean, I think, but this all get, but this gets into some pretty, this is all philosophical territory. It's just
Exactly.
orbiting around this notion of subjective probability, right? So, if you ask a person who hasn't thought about the problem very much, well, actually, I should say also that, I mean, I was raised Jewish, and Jews don't really have hell as part of their theology. So that's worth knowing. Um, but so I'm kind of an outsider actually when it comes to discussions about hell.
Yeah.
But my like I mean, so I feel like we can't actually. Yeah, we probably shouldn't talk too much about it since
Yeah.
I'm not a hell expert.
Yeah.
Sam,
Well,
are you a
I'm a
hell
hell
expert,
expert
Sam?
because I was raised Catholic.
Oh, okay,
But I
all
was raised
right.
by Jesuits, so maybe not. They don't lean
You
heavily into
you were
that.
raised by Jesuits.
Yeah, I know. I always think it's like a pack of wild Jesuits out in the woods, you know. But no, no, I love Jesuits. They're amazing. I was raised in a Jesuit church. I was brought up in a Jesuit church.
Okay.
Okay,
So yeah, you
well,
should tell me about it, not the other way around.
yeah. Well, in a way, Pascal's wager is based on practical reason, like what you should bet, but this is supposed to be based on evidence that, if it's true that Sleeping Beauty gets some evidence by waking up that it's two-thirds tails, then another way to think about it would be, if you were asked to bet whether the many worlds interpretation of quantum mechanics was true, and if you bet an infinite number of Erics were betting an infinite number of dollars, then they would come out ahead betting yes
Well,
on.
yeah, but just to be clear, I mean, there's the whole point of the interpretation of quantum mechanics is that they're all, I mean, there are competing interpretations of quantum mechanics, but ultimately they don't affect experimental outcomes. So it absolutely, like, there's no way to say for sure that there's an infinite number of universes,
Oh, right. Yeah, right.
right?
This is well,
So there's no way to resolve that. There's no way to resolve the bet.
this is a well, that is true, but this is a probabilistic argument that we should be almost certain. And so some people might want to not
Yeah, but
say
there's no
two-thirds.
consequences.
Well, yeah, I mean,
I mean, that's why
philosophy.
Pascal's statement about the existence of God, in that case, hell makes the consequences very profound. But in the case of but I mean, because you die and then you, I guess, are judged and go to either heaven or hell. I mean, there's a time limit beyond which there are consequences for your bet, your wager. But there's no time. I mean, there's never going to be a moment where people say, "Oh, well, there really is a quantum infinite number of universes." I mean, I guess one could imagine that there's some future grand unified theory that does elaborate on that. So I guess really you're betting on future progress in physics. But assuming that our current understanding of quantum mechanics never improves, then the bet there's no outcome for that particular bet.
Right. You couldn't resolve it. Um, True. But we like to think about things like that over here in philosophy.
Oh, you see, okay, this gets back to like one of our very first conversations, which is you like to think, as philosophers like to think about questions that don't necessarily have an answer, whereas scientists prefer to think about questions that very definitely do have an answer.
Well, they do have an answer. I mean, I would say there is an answer whether the multi-worlds interpretation is true or not,
No,
whether there's
okay, so
other
for me,
universes.
because it's untestable,
Yeah.
it it's not a valid question.
Well, no, okay. Now I'm going to argue with you. It's not, I would say, for me, it's not a valid question for scientific discovery if we think, scientific claims should be falsifiable or whatever. But I don't think that means it's not a meaningful or contentful question. So this is another thing debated in
Ah,
philosophy. Can you
so
formulate questions that are in principle meaningful but untestable? Can our language formulate something that could never be resolved?
Well, I mean, in language, you can formulate questions that are nonsense questions. I mean,
Yeah,
like arguably, like, what is the meaning of life? It's a grammatically correct question, but it has no answer,
right,
right? I mean,
right. You
so
can,
this is
but
actually one of the, I mean, we haven't talked about this explicitly, but yeah, this is one of the reasons why, as a scientist, I'm always slightly skeptical about philosophical questions that feel almost more like linguistic games. Yes, you can rearrange words to make a question that sounds interesting, but but there's no way of answering it, or from another perspective, it's simply a nonsense question.
right.
Um,
So
yeah, I
yet
mean,
again, I think we've come around to another idea for an episode in one of our episodes. So I think we should leave it for there. I think we're probably
okay.
past time, but thanks for listening.
Yeah, so I'm Eric, and that's Sam, and we are the Boltzmann Brains. Also, if I'd like to hear us talk about some topic in a future episode, feel free to drop us an email at thebbrains@gmail.com. Thanks for listening.